When someone says the word vector, a number of things might come to our mind, primarily an arrow with a tail and a head. In linear algebra, the ideas are similar, but it's a lot more detailed. Even there, we can talk about the vector addition using the triangle law, and also the scalar multiplication, which can essentially elongate, squeeze, or even change the direction of the arrow. Now, in general, if we say the word vector, it will be reasonable to visualize it as an arrow on a coordinate system where the tail sits on the origin. Here, the coordinates show the exact address of the tip. In other words, how to move from the tail to the tip. In this case, 2 units along the x-axis and 3 units along the y-axis. Now it's interesting to note that the vectors can also be stuffs like complex numbers or even set of polynomials. Now let's recall what we had talked about the addition of vectors and scalar multiplication. These two operations play an important role in the entire linear algebra. Now when we are talking about these operations, let's now think about a set of vectors like a straight line in this case passing through the origin. Each point on the line represents individual vectors. Now addition of two vectors on this line clearly gives us another vector which also lies on this line. Similarly, multiplying the vector with a scalar also gives us a vector which lies along the line. Also note that the origin lies on this line. In other words, the 0 vector. Now note that if we apply the two operations on the vectors on this line, we get a vector which also lies on this line. This collection of vectors forms a vector space, which is a one-dimensional line in this case. Now under addition, a vector space has the following properties. The first being the commutative property, where the order of the addition does not matter. Next, we have the existence of a 0 vector, which also serves as the additive identity. That is, adding any vector to it gives the vector back. The next important property is the existence of an additive inverse. And finally, we have the associative property. Now, if we talk about the scalar multiplication, we also have a few properties to note, like the distributive properties, the associative property, and the application of 1. Now, when we talk about scalars, this can not only be reals but complex numbers as well. Now, to add to the definition of the vector space, we must deal with those scalars which belong to a particular field associated with the vector space. Now if we talk about the examples, the space R2 can be considered one such. In fact, the general Rn space. Apart from that, set of polynomials of degree 4 or less, or even a set of m cross n matrices.